All right, so some examples with matrices. This is a matrix, again, rectangular arrangement of numbers in rows and columns. The plural of matrix is matrices. The matrix below shows the hours Jeff, Tina, and Eric worked on Saturday. So already into a problem here. So again, where they worked, right, and their names. So apparently they work multiple places. Aguas, I don't know what that is. You identify the size of the matrix by the number of rows and columns. The matrix above is 3 row, 2 columns, so it's a 3 by 2. So again, we list rows first, then columns. So 3 by 2. Each number in a matrix is an element. So 1, 2, 3, 4 elements in this one. Matrices are equal if they're the same size and the elements in corresponding positions are equal. So same size, same shape kind of thing, right? Like these two. You notice here 5 minus 1 is 4, right? So they all match up. So you can use matrices to organize data. This make it easier to perform calculations on the data. Okay, so first off, we'll start with adding matrices. And so here, again, they have to be the exact same size and shape to add or subtract them. Multiplication, no, because we use that scalar out front. But addition, subtraction, yes. Exact same number of columns and rows. So these two I can add. So 5 plus negative 5 plus negative 3 is negative 8. 7 plus negative 4 is 3. 2.7 plus negative 3.9 is negative 1.2. You follow me here? Negative 3 plus 2 is negative 1, so there you go. Same thing with subtraction. Just got to be careful to make sure you know you're subtracting right. Like 2 minus negative 1 is 3. 4 minus negative 6.5 is 2.5, so on and so forth. So it says, what is the sum or difference of each? And again, these two are straightforward, right? 5 plus negative 9. And 3.2 plus negative 1.7. Negative 4.9 plus negative 11.1. And over here, negative 4 minus negative 5. 3 minus 0.5. And I'll give you a minute to look that over there if you want to pause. But here's your answers right here. So actually do the work just to make sure you're doing it right. Then explain why you cannot add or subtract matrices that are not the same size. Well, I mean, you could try it, right? But if they're not the same size, you don't know where the corresponding elements are, right? So if you try to do like add this one and this one, you wouldn't know what to add to what because they don't have corresponding positions. Next example, multiplying by a scalar. So what you'll have is one number out front multiplied by everybody inside. It's like super distributed property. So 3 times 4, right, goes there. 3 times 1 goes here. So keep them in the same position, otherwise it's technically wrong. 3 times negative 1.5. 3 times negative 6. And that's actually the answer. Same thing here. I want you to do each of these. So here are, right, 3 columns by 1 row. Here is 2 columns, 2 rows. So again, what that really looks like, and you can pause me here and come back and do them or whatever. So I'll take that, and I'm gonna go ahead and just do the work. There we go. Oh, I like a thicker pen. There we go. Alrighty. So if I take a look here, I've got negative 2 times negative 3, right? So that is 6. And I've got negative 2 times 7.1, and that's negative 14.2. And then finally, I didn't leave enough room here, really, did I? You know what? I'm going to make that bigger. This. There we go. Negative 2 times negative 3 is positive 6. Negative 2 times 7.1 is negative 14.2. It's a 4, I promise. And then negative 2 times 5 is negative 10. And that's the answer. That's all there is to it. And B, same thing. Just keep them in the same position. Right down here. So, again, you can take a look down here, and it says insert reduced. Ignore that. That's not a big deal. So what we're looking at here, and this gets back to the idea of what these were originally for. It says, use the weather chart below. Which city has the greatest average number of clear days in a full year? I'm going to scoot this up here. We're looking for clear days. I'm going to write that off here so I remember. Clear days. Okay, so we can take this data right here, right? Phoenix has clear and cloudy, Miami clear and cloudy, Portland clear and cloudy, and then same 3 cities in a different time frame. And you can see here, I'm really going to end up adding these 2 matrices between the two. So let me switch my pen here. So really, we're going to be adding, so we know the clear and cloudy for both. And so we take this right here, literally 102.41, right? 43.58, 5582, and you just transfer it straight down into the matrix. The matrix. Sounds like fun, right? Alrighty, so then we just go through and add them up. So we can say Phoenix, clear, clear, right, goes here. Miami, clear, clear, goes here. Portland, clear, clear, goes here. And then go back. Phoenix, cloudy, cloudy, goes here. Miami, cloudy plus cloudy. And Portland, cloudy plus cloudy. And there's your final matrix. And you can see there, the work I did for it, or they did for it. Find the greatest average number of clear days in a full year. Well, again, look at this, the biggest number, 212. So that's Phoenix had the greatest average for the whole year of clear days, 212. I just went in and brought the data over from the last page. So again, this matrix, right, this one plus this one is going to yield this, right? So we have clear and cloudy. So clear and cloudy goes right there. And we're looking for, so cloudy's this column, which one has the greatest average number of cloudy days in a full year? Well, we're going to look for that biggest number, and we can see, we know this represents Portland cloudy right here. So 165, Portland cloudy wins out on that one. And just in case you didn't think I was going to do it, right? Welcome to the Matrix. There you go. All right, so I think I'm funny. All right, have fun.